Quantum computing.
Quantum computing.
Quantum computing.
Quantum computer.
Quantum computer chip.
This is a quantum computer.
The UN has named 2025 as the International Year of Quantum Science and Technology on the occasion of 100 years of quantum mechanics. And it's an exciting time in quantum computing as we reach towards the long-sought goal of quantum advantage. This is a critically important concept in quantum computing. It's basically the reason we're building quantum computers in the first place. But what is quantum advantage exactly? In this video, we'll help you understand exactly what quantum advantage is and what so many people get wrong about it. Classical computers, like your phone or your laptop, are extraordinary machines, and they're capable of doing truly amazing things. But there are some computational tasks that classical computers struggle with. One example of a problem that we think is hard for classical computers is factoring, where we're given a positive integer, and the goal is to express that number as a product of prime numbers. For example, the factorization of the number 91 is 7 times 13. That one is easy because 91 isn't very big. You could even solve it on paper. Now, how about a larger number? What about 2,595,317? Well, you'd probably need a computer to help you solve that one, like I did, although it didn't take too long to compute. Turns out the prime factors are 1609 and 1613. Now here's another one. The number shown on the screen is called RSA 1024, and it has 309 decimal digits, or 1,024 bits if it's written in binary notation. Nobody knows the prime factorization of this one. In fact, in 1991, RSA Laboratories offered a cash prize of $100,000 to anyone who could figure it out. And to this day, nobody has. Because every classical algorithm for factoring that anyone has ever come up with takes too long. People just don't live long enough to be able to wait for these algorithms to finish factoring numbers of this size. And that's not for a lack of trying. A lot of very smart people have tried to come up with efficient algorithms for this problem. Simply put, it's a highly complex problem for a classical computer to solve. Or so we think. In 1994, however, Peter Shor came up with a method that allows a quantum computer to solve this problem quickly, so long as we can build one that's up to the task. So how can a quantum computer succeed where classical computers fail? Quantum computers harness quantum mechanics to compute by different rules than classical computers do. They don't perform operations faster than a classical computer, but they perform different operations that a classical computer can't. And sometimes those operations offer a faster route to a solution. The details are complicated, but that's the idea. As it turns out, it's an extremely difficult technological challenge to build quantum computers. And after over 30 years, we're still a long ways away from being able to build one capable of factoring a number like RSA 1024 using Shor's method. But the technology is developing rapidly. And we expect quantum computers to be useful for a lot more than just factoring large numbers. Another task that we believe quantum computers will be useful for is simulating nature, which appears to obey the laws of quantum mechanics. Quantum mechanics is complex, and sometimes classical computers can struggle to crunch the numbers to figure out what nature is doing. But quantum computers play by different rules. Quantum computers don't need to crunch these numbers per se. They can simply mimic nature rather than approximate it. And that's because, just like nature, quantum computers are quantum. And the potential here is enormous, not just for understanding physics, but for designing new materials and medicine, for instance. Okay, so that's all fine and good. But do today's quantum computers actually allow us to solve problems that we can't using classical computers? The answer is no, not today, not yet. But the technology is advancing daily, and soon we expect it to start paying dividends. This brings us to the subject of quantum advantage. Now, the term quantum advantage means exactly what it sounds like. Quantum computing actually paying off. So when a quantum computer allows us to solve computational problems more efficiently, more cost-effectively, or more accurately than we can with classical computers alone. That's simple enough in principle, but there are some important subtleties. First, it is a misconception that quantum advantage is about quantum computers versus classical computers. In reality, it's quantum computers plus classical computers versus classical computers alone. Just look at these racks of classical computers here, which are all needed to make this quantum computer work. The point is not to beat classical computers with quantum computers, it's to enhance classical computing with quantum computers. Quantum computers won't replace classical computers, they need classical computers to work. Second, it's another misconception that quantum advantage can be definitively proven with one demonstration. That's not true, because that's not how science works. The philosophy of science tells us that scientific claims are not provable statements. They are hypotheses subject to falsification. Through repeated attempts to challenge and disprove a hypothesis, we may gain confidence in its truth. But absolute certainty remains impossible for all scientific theories. Naturally, if we have a particular problem we'd like to solve, we pick the best method available to us, whether it's the best in terms of the time required, the cost in dollars to find a solution, or some combination of the two, or something even entirely different. But we never know for sure that a better solution isn't just around the corner, waiting to be discovered. For example, we don't know for certain that an efficient classical algorithm for factoring won't be discovered tomorrow. We really don't think that will happen, but it could. You can see how the dynamic landscape of algorithms can change the usefulness of a technology very quickly, as we have seen in the AI space. This applies equally well to problems having quantum solutions. When we reach the point when we believe that a quantum device may have provided an advantage over classical computing alone, this belief will be a hypothesis. We must then allow classical computing to respond, and under no circumstances should it be underestimated. In fact, we fully expect classical computing to put up a strong fight, not only because classical computers are extraordinary machines, but because people continue to find creative new ways to use them. Initially, hypotheses of quantum advantage will probably be eclipsed by new classical methods, and this should not be seen as a failure of quantum computing. Rather, what it means is that further work on the quantum solution is needed, so that it once again becomes the better alternative. This sort of back and forth is very healthy, in fact, and it should be encouraged because it will lead to improvements in both classical and quantum computing. So don't expect a definitive, incontrovertible claim of quantum advantage to stand. Instead, there will be some competition. And don't imagine classical computing will just roll over. Here at IBM, we expect to start seeing serious claims of quantum advantage within the next 2 years. And then we'll have to wait and see how classical computing responds. And the last point I want to make is that for a reasonable hypothesis of quantum advantage, we need to trust that the quantum computer is giving us the correct answer. If you and I solve some math problem, and I solve it faster than you, but I get the wrong answer, there's no advantage in that. The same goes for quantum computing, except that sometimes it can be quite tricky to know if a result is correct. For a problem like factoring, it's easy to check the correctness of a solution. But for other problems, it's not always that simple. A great example is the random circuit sampling demonstration recently performed by Google with their new quantum chip. This is the task that you may have heard about in the news that they estimate would take 10 septillion years for a classical computer to solve. What this task is, quite literally, is to run randomly generated instructions on a quantum computer. On its own, that's probably not a very useful thing to do. But that's not the point. The point is that we don't know how to get a classical computer alone to predict what happens when random instructions are run on a quantum computer. But on a quantum computer, you can just run them. So it's a hypothesis that the quantum computer is doing something beyond the capabilities of classical computers alone. The trouble, however, is that for this particular problem, running random instructions on a quantum computer, we don't actually have any way to verify that the quantum computer ran the random instructions correctly. That's why, before making claims of advantage, we first need to establish trust in the device itself. Just like in any experiment in science, where we must validate the instrument before using it to make discoveries, quantum computers require rigorous demonstrations that build confidence that their outputs are accurate, especially for problems where classical verification isn't feasible. This is what IBM demonstrated in 2023, and what we called the evidence of utility of quantum computing in the pre-fault tolerant era. The demonstration that we can trust the outputs of a noisy quantum computer whose outputs lie beyond brute force classical simulation. This is huge, since this ensures that these methods can be relied upon for exploring quantum advantage. But don't take my word for it. Read the paper. I'll link it below. Now, we've already talked a bit about how the search for quantum advantage will likely play out. There will be demonstrations of what quantum computers can do, but then classical computing gets its turn. There will be hypotheses of quantum advantage. And at the start, it's reasonable to expect those hypotheses to be falsified as creative people come up with new ways of approaching the relevant problems with classical computers. But quantum computers continue to develop, and people find new ways to use them as well. And one day, perhaps not too long from now, a hypothesis of quantum advantage will be met with silence as classical computing fails to respond. And as long as classical computing falls short, we'll have a quantum advantage. Do I have a bias? Of course I have a bias. I work for IBM. But what I'm saying now should not be controversial. Scientific progress is sometimes slow. Sometimes it's unpredictable. But it is always rewarding. Thank you for watching, and be sure to subscribe to this channel if you want to learn more about quantum computing and stay up to date on the exciting new advances that are surely on the way.